Okay, you're here with me. We're in Chapter 11, Section 1. So we're at 11.1. We're looking at molar volumes of gases. And now I'll start with this image. So this is 11.1 in your book. So right here, we have equal amounts in moles are N, what we're using N, of oxygen and of hydrogen. So I have 1 mole of oxygen gas, I have 1 mole of hydrogen gas. One thing we want to know while we're looking at this is do ignore in the image the size of the molecules that they're showing you. Now, the molecules are different sized, but in reality, as we know with gases, these molecules are so incredibly small compared to the volume they're occupying, we cannot even see them. That is how our kinetic molecular theory works. All of our ideas about ideal gases work based on them being very, very tiny in the space that they're occupying. Regardless, notice we have 1 mole of each of these. If we have 1 mole of each of these, and they're at similar conditions, well, not similar, the same conditions, say we are at a temperature of 0 degrees Celsius and a pressure of 1 atmosphere, well, then these 2 gases are going to occupy the same exact volume. So same amounts of gases at constant temperatures and pressures are going to occupy the same volume. Now notice they still have different masses. Oxygen is still heavier. Notice where that mass is coming from. That 32 grams is the molar mass of oxygen. So 1 mole of oxygen still has a mass of 32. 1 mole of hydrogen gas, diatomic, still has a mass of 2.02 grams, but they have the same volume. They occupy the same volume. So notice what it says here. 22.4 liters of each gas contains the same number of molecules, 1 mole of each. The mass is different, though, because the mass relates to the molar mass. The volume is dependent upon these 2 things, the temperature and the pressure. That is what affects the volume of any gas. If we remember back to our combined gas law, we had P and we had V over N1T1, and that, again, was equal to PV sounds like Finn, P2V2, N2T2. Okay, so we found that condition was true. So if we zone in on our volume, again, what is affecting the volume of a gas? Well, it is the pressure on that gas, the temperature of that gas, and the number of moles of that gas. Now, it does not matter what the identity of the gas is, only how much of it there is in moles, not mass, in moles. So those are the 3 conditions that affect our volume. And if we look at this 22.4 number, this 22.4 number is actually derived from this equation, because what we can say is that P1V1 over N1T1 equals P2V2 over N2T2, but we could also say that this is always equal to a constant, and the constant we use is a constant called R. So if we take this equation and rearrange for V, V would be equal to R NT over P. So if we take a pressure of 1 atmosphere, and we take moles, 1 mole of a gas, and we take a temperature of 0 degrees Celsius or 273.15 Kelvin, and throw in our constant for R, which we could look up right now, we're not really concerned with it, what we'll get for that volume is that 22.4 liters. So this is a derived value that we can use anytime we have gases at standard temperatures and pressures. So just so we have, this picture's kind of goofy, but just so we have some idea of what size of gas we're talking about, this electronically derived cube is 22.4 liters. It is 1 mole, again, of any gas at STP. Notice the size of it, a little bit bigger than a basketball or a football, a real football or American football, whichever one you like. So notice, by the way, what this value is going to allow us to do. It's going to allow us to look at the volume of a gas in liters at STP and convert it into a number of moles. Remember, from moles, we could always go to mass if we need to, and we'll write a whole derivation for that later. Or we could take the moles of a gas, and we could convert it into a volume. So if we're at standard temperatures and pressures, again, 0 degrees Celsius, pressure of 1 atmosphere, we can use this as a conversion factor. In your book, it has a couple of these, so let's try them. So this is number 4 of the section review, I believe. Pull over number 4. It says, how many moles of oxygen gas are there in 135 liters of oxygen at STP? So if I have 135 liters of oxygen, again, at STP, now what they're expecting us to know, and what I'll expect you to know as we go forward, is at STP, 22.4 liters is the volume occupied by 1 mole of any gas. So this is now my conversion factor. We're going to use this conversion factor just like we've used any other conversion factor. we're going to throw it into our equation to cancel out the units we don't want. We're trying to get rid of liters in this case, so I'm going to divide by 22.4 liters of oxygen, and I'm going to put the value of 1 mole of oxygen on top. That is it. 135 divided by 22.4, that's approximately 6 moles of oxygen. If you want to punch it in your calculator, get a little bit more accurate number, you can. It's about 6 moles, so that's what we're going to be doing with it. Now notice we can go in the other direction as well. Number 5 says what volume will be occupied by a certain number of moles of methane. And again, in these instances, I'm not really concerned at all of what the identity, I'm going to write it down, but it doesn't matter again if it's methane or if it's oxygen, because all gases occupy the same volume at the same conditions. So I have my moles of methane. This time I'm having moles and I'm solving for a volume. So I'm going to take my same conversion factor, 22.4 liters over 1 mole, again because we're at STP. This time my volume is going to go on top, 22.4 liters. This time I'm talking about methane over 1 mole of CH4 of my methane. One thing I'm going to be a little bit more careful with in this particular problem is that it asks for milliliters. Now the reason it asks for milliliters is typically in lab we're not going to be measuring volumes of gases. If we go back to that image, a liter of a gas is quite a lot of gas. So typically we'll be collecting gases in values of milliliters. So we do have to convert from liters to milliliters. I'll do that. So 1 liter of a gas, 1 liter is 1,000 milliliters. And that should be a conversion factor that we know. Just like 1 meter is 1,000 millimeters. Hopefully we know these things. So my liters units cancel, my moles of methane cancels, and now I should get an answer in milliliters. If you do the math, you should get a value of, I believe it is 78.4 milliliters of methane. Okay, so not too terribly bad. We know at standard conditions, any gas is going to occupy, 1 mole of any gas is going to occupy the 22.4 liters. So, again, I'm just writing it down so that it sticks in your head. At STP, 1 mole of any gas is 22.4 liters. Since all gases, equal amounts of gases, occupy the same volumes at the same pressure and temperature conditions, the other nice thing that we can do with this is we can use it to help us solve our relations in already balanced chemical equations. Oh, but before we do that, one more slide I wanted to show. Notice at 1 atmosphere of pressure, 0 degrees Celsius, a volume of any gas is going to be 22.4. And notice what this is saying. Again, my German's not the best, but I believe what it's saying is at 0 degrees Celsius, 1 atmosphere, any gas, and again that can be any gas, hydrogen, helium, nitrogen, oxygen, CO2, SO2, so carbon dioxide, sulfur dioxide, is always going to occupy 22.4 liters. Notice if we put in more moles of gas, obviously the volume gets better. I just like this image, and not often we get a good German image to use. Okay, so we already know that equal volumes or equal amounts of gases occupy equal volumes of gas, equal volumes. So what this is telling us, this is the reaction between hydrogen gas, which there's 2 little bubbles because it's H2, reacting with chlorine gas to make hydrochloric acid over here. And if we write this as a balanced equation, what you'll notice is that 1 molecule of hydrogen, reacts with 1 molecule of chlorine to give us 2 molecules, 2 hydrochloric acid molecules. That's what we have talked about in molecules, and often a lot of times we've said 1 mole of hydrogen plus 1 mole of chlorine, and in this case give us 2 moles of hydrochloric acid. Notice that's what it is saying right here for Avogadro's law, that the volume and the number of moles are directly proportional. So we can use a balanced equation for converting between moles, but we can also use it to convert between volumes. Notice what it says, 1 volume of hydrogen gas reacts with 1 volume of chlorine gas to give us 2 volumes of hydrochloric acid gas. So if this, for instance, was at STP, at 0 degrees Celsius, 1 atmosphere of pressure, 1 mole of hydrogen gas would be 22.4 liters. And that would react with 1 mole of chlorine gas, which would be 22.4 liters. And that would give me 2 moles of hydrochloric acid gas, which would be 44.8 liters. So I can use those ratios to help me solve a gas problem as well. Notice another example of that here. And again, this only works, we have to have gases, right? So we have hydrogen gas, oxygen gas, making water vapor. Notice 2 molecules plus 1 molecule equals 2 molecules here. So they also have it in moles, they have it in volumes. So 2 volumes of hydrogen gas will always react with 1 volume of oxygen gas to get 2 volumes of water. So we could use this for doing some types of stoichiometry. We could say, well, if I have 5 liters of hydrogen, over here I could say, well, how much water vapor? So I have some hydrogen fuel cell. I have 5 liters of hydrogen in my hydrogen fuel cell. How much water will that produce? Well, instead of converting this into moles and everything else, I can just use the conversion factors that are here. This is telling me that 2 hydrogens, in this case 2 liters of hydrogen, will produce 2 waters. In this case, 2 liters of waters. Because again, equal amounts of gases occupy the same volume at standard conditions. So in this case, it'll make 5 liters of water. That's pretty awesome. That way, that has saved me a lot of conversions. I don't have to convert them into moles, do the molar ratio, then convert them back out. I can use the mole ratio as a volume ratio as well, as long as we're at the same conditions across the equation. So if you would, let's just look at some volume problems using that Avogadro's law. So here we say, what volume of hydrogen, so I'm going to put a big question mark above my hydrogen, is necessary to react with 5 liters of nitrogen. So I have 5 liters of nitrogen to produce ammonia. Notice a constant temperature and pressure. That's so important in this problem. If the conditions change, then we have to calculate this, and it gets a lot more difficult. But if I have 5 liters of N2, and I look at my relation, again, I can use my molar relation as a volume relation as well, as long as we're talking about gases. One of these makes 3 of these. So 1 liter of nitrogen gas will always produce, by the balance equation, 3 liters, or react with 3 liters of hydrogen gas. So I need 15 liters of hydrogen gas to react with it. That is what the ratio is telling me. I could solve number 2 the same exact way. These should be pretty easy problems for us to solve now that we've done mole ratios before.